Good morning. Great to be here. I just arrived after a long trip, so I might fall asleep right in front of your eyes, but I will do my best. So gravitational wave astronomy in the Decihertz band, that is my talk today. And I won't tell you much about the detectors, even though the first one I have to show, and afterwards on Thursday you will hear more about the detectors. The science is amazing, so let's keep focused on that in this talk. So this is, I think, the starting point of Decihertz gravitational wave science. That's when people started to really get interested in the details and studied sources. So the Big Bang observer was proposed, I wouldn't say proposed, but it was a concept that was kind of analyzed and conceived in 2003, essentially, by Stirl Finney and a group of scientists at that time. And so essentially, that is an enormous detector where you would have to deploy all around the sun satellites that work together to analyze all kind of transients like the astrophysical foreground, but with the goal, and that was the task that was given to the group, with the goal to measure the primordial background. So the question really was, even if the background were really small and weak, for example, produced by slow roll inflation, what would you need to detect it? And that's the concept that they came up with, the Big Bang observer. Now, okay, somehow, I'm just too far away. Okay, so now in the early years, there were then a couple of studies essentially around this detector. And of course, already then it was found that there's much more you can do with it, not just detecting the primordial background. You would also essentially see all compact binaries in the band and resolve them. You would, and this means here composed of neutron stars and black holes. I will come to the white dwarfs in a bit. You would even do very nice weak lensing measurements, essentially looking for deviations. You know, you try to establish a redshift distance relation, and then you see the spread around that relation when you observe your sources. And that spread, if it's too large, if it cannot be explained with the statistical errors of your measurement, then it would be explained by weak lensing. And so that was essentially what they proposed. You would observe a huge number of double white dwarfs. You could make Hubble constant measurements and binary Newton star pre-merger alerts. So all of that was already laid out in the early years. Now, the challenge, however, was really quite, extreme. So here you can see essentially the landscape from 10 to the minus 10 to 10 to the 5 hertz of certain spectra of sensitivities. And the primordial inflation is really the level that Big Bang observer wanted to get to. And you can see, I mean, here you see Einstein telescope and Cosmic Explorer, which are also more recent concepts. So in the early days, we were looking essentially at these curves here. And then they had to propose something that dives all the way down, like by so many orders of magnitude, to this primordial inflation background. And of course, when then this Big Bang observer was kind of put on paper, it was also immediately clear that this would be an extremely challenging thing to realize, hugely expensive, and technologies that are far from doable. Okay. Now, in the same year already, Farmer and Finney published a paper where they produced plots like this one here, where essentially you can see the accumulated energy of white dwarf binaries. Now, why are the white dwarf binaries so important in this discussion? Why don't we talk about them in the same way that we do talk about binary neutron stars and black holes? Well, the point is the following. It is connected also to the question like why LISA cannot dive down arbitrarily into the backgrounds. Because at some point there's a fundamental problem. You have so many data points that you can collect within a year or a few years compared to so many signals that you have in the data and with all the parameters that you have to estimate and then subtract out if you want to see anything that is weaker than this background. So if you have more signals and let's say more parameters that you need to estimate than samples in your data, then it doesn't work anymore. You're stuck. You're hitting a fundamental limit that you cannot overcome no matter how sensitive your detector. Okay, so a LISA detector that is 100 times more sensitive than the one that they are going to build will not give you better stochastic background sensitivity where you hit the essentially fundamental limit posed by the white dwarf background. Already the galactic binaries are so numerous that they are already enough to give you a fundamental limit to the LISA sensitivity to stochastic backgrounds. So then if you look at this curve, you see, however, that this energy density is falling off very sharply towards higher frequencies. And that is, of course, because the white dwarfs start to merge. Now there are different types of white dwarfs, and not all of them merge at the same frequency. So there are certainly also question marks here still. But the point is that looking at these spectra, the Decihertz band seemed to be ideal, because the other thing that you want always in combination to avoiding this foreground is to still observe at the lowest possible frequencies, because that's just how the energies are distributed. You know, if you look at the spectral density of backgrounds, they are just becoming stronger at lower frequencies, so that helps. So what you want is you want to go to the lowest possible frequencies, but not too low that you are like dealing with this white dwarf foreground. And so that led then to the Decihertz band to be the one that people should aim for. Oh, these are different types of white dwarfs, like cobalt, oxygen, oxygen, neon, and what, you know, all of these things. So helium. Anyway, so now, since it was realized very early that Big Bang Observer would be something that you may or may not see in your lifetime, people came up with other ideas what you could do. And I will not talk more about this here, so this is my only slide on all these detectors, but there is the satellite-based long baseline solid test masses. That's what I mean with, you know, DeSiGo Big Bang Observer. Solid test masses in the sense that we are meant to put a cube in the side of the satellites and then reflect light from them. There are also the satellite-based long baseline atom clocks or atom interferometers. So they are really kind of almost the same. Atom clocks, atom interferometers, it is more, you know, how you look at them. So the atom clocks means you want to do something like PTA just with artificial neutron stars. And atom interferometers are like you are doing almost the same, just that the atom configuration in the satellites is a bit different. In reality, the noise limitations are almost identical in these two cases, because you do have to communicate with laser links between these stations. And so they are all kind of ending up with similar noise budgets compared to the LISA detector, for example, LISA type detectors. Okay. And then we are also starting to discuss lunar gravitational wave detectors. And then there were exotic technologies proposed. The latest one, the frequency comb detectors. These are all relatively compact detectors. Diamond detectors, where they want to produce little crystals of diamonds with like nitrogen defects inside, and then do some superpositions of the states of spin states, I believe, of these diamonds, and superfluid helium. So all of them, you know, when you look at them, this list, the list is so long because we are really in this embarrassment that we don't know how to build a Decihertz gravitational wave detector. Whatever you have in mind, it is going to be extremely challenging because the technologies are so far away from what we can do. Now, all the terrestrial detectors, that's the one thing that we have learned in the meantime, they are not feasible. And there are also fundamental, truly fundamental limitations coming from this, because the foreground of terrestrial gravitational noise that people always believe can be subtracted, there are fundamental limitations to how well you can subtract them. No matter how many sensors you put, it's just a statistical impossibility to subtract out all of this foreground to be able to do Decihertz gravitational wave detection with terrestrial detectors. Okay, so we have to go into space on the moon. That's fine, that's already good to know. Now, the one thing, I mean, Bruce already mentioned it briefly, what we can do, and this is one of the strong suits as well of Decihertz detectors, we can, they're in the middle between LISA and terrestrial detectors. And so they are the ideal multi-band partner. You can construct a multi-band science case also between LISA and terrestrial detectors, but it's like something not so strong and maybe unlikely to be done in the end. But as soon as you put a Decihertz detector in the middle, it is a likely and a very important part of the science case. The combined measurements, especially with the Earth detectors, which are guaranteed to exist. But maybe in the future, there will also be the possibility to do multi-banding between LISA-type detectors and Decihertz detectors. And so that is for sure very interesting because it helps you with pre-merger alerts, with parameter estimation, and so on and so forth. So now, more recently, we restarted Decihertz science case studies. And that was connected to the lunar gravitational-wave antenna, where I'm personally involved in. And so one of these papers that we wrote is a mission studies and science case white paper, if you want, about LGRBA, where you find a quite extensive discussion of the science that we can do, multi-messenger and gravitational wave. Now, to start first about the detection horizons. Now, this is you can see here for the Einstein telescope, here for LISA, and here in the middle for LGRBA. Now, of course, if you plotted this for DeCigo or BBO, the values would go up by a lot here, so they would have an immense detection horizon. But the structure, more or less, the peak behavior in this at these values of total binary mass is still characteristic for any Decihertz detector, essentially. Here you can see, of course, what happens with Decihertz detectors, that you start to observe intermediate mass black hole binaries even at very high redshifts. And we know that these probably play a very important role in the formation of the larger black holes very soon in our universe. So also about pre-merger alerts. Now, you have very long observation times in the Decihertz band of Newton star binaries. And now, for LGRBA, the science is not, it's there, but they would see as many Newton star binaries as LIGO and Virgo is seeing today. So that is not really the perfect detector for that. But if you think about DeCigo or BBO, they would essentially see all binary neutron stars. And so essentially for all of them, given the long observation times and the modulation in phase and amplitude that you have of your signals because of the motion of detectors in that time, you can do very precise, always sub-squared degree localization of these sources. And that, together with the pre-merger alert, gives you really unique opportunities for multi-messenger astronomy. Then, white dwarf. Yeah, a bit larger. I think it's sub 0.1 square degree, but yes. So, of course, now what we are talking about is even, for some of these systems, for example, the same is also true for white dwarf binaries. You start to be able to localize them, not only, telling which galaxy they are located, but also where inside the galaxy they are located. So that's the kind of precision that you are aiming for now. That also makes it interesting. White dwarf binaries is the completely new, and the merger especially, it's a completely new phenomenon that you have access to in the Decihertz band. And so even with LGRBA, which is maybe the first step of Decihertz observatories, already here, you can see, again, compared to LISA, which has an horizon that extends just, a little bit beyond our own galaxy. But with a Decihertz detector, even not like the greatest one, you would already see white dwarf binary mergers up to tens of megaparsec, which is enough to actually have mergers observed. Now, first of all, these mergers can be then located in their galaxies, so you always get like a redshift distance pair out of it, so you can do Hubble constant measurements. But then this is also connected to the supernova type 1a, where you might know that there's this ongoing debate between what is the progenitor. Is it double degenerate? Is it single degenerate? Or is it a mix of those? And what can we learn? Maybe can we improve our cosmological distance ladder, where supernova type 1a play an important role? Understanding more about the progenitor of these events. So this is a huge topic to be addressed in Decihertz science. Just now in a more recent study, you can see that you would really be able to do very good distance estimates and scalarization here in square degrees, like 10 to the -5, 10 to the -3, for a significant number of sources. Okay, so that is for sure a unique opportunity. And then maybe surprisingly, core collapse supernova could be detected with Decihertz detectors, maybe better with Decihertz detectors than with terrestrial detectors, because there's this huge memory effect, which is connected to asymmetric ejection of matter and neutrinos from that core collapse supernova. And you know, these, not everybody might be familiar with these time frequency plots. They looked a little bit different in the past, but you might know that in the simulations, they never really managed to make them explode. And that is a more recent step forward that they made. So now people actually know how to make supernovas explode in simulations. And that's how the time frequency plots look like when you have an explosion in your simulation. And so there you see this huge memory effect, which in the past was never present in the results. It is leading to this huge shoulder at low frequencies of these signals. And here it's not really reliable because the simulations don't really go down to the Decihertz band, but you get the idea that there's a huge amount of energy at these low frequencies that could be detected with Decihertz detectors. And almost last slide. Another event that is kind of unique to the Decihertz band are the tidal disruptions with white dwarfs. And they can be tidal disrupted around black holes. They can be tidal disrupted together with a neutron star. If they are close enough, then they might be detectable, but it is the waveform models at the moment are not so good. Probably if you want to detect a tidal disruption event, for example, around a black hole, what you would have to do is you would have to take the full waveform, when the white dwarf circles in, and then in the end, you see the disruption as a weaker signal, of course, in the waveform. The same with the Newton star white dwarf binary. Essentially, the in spiral is the signal that gives you the detection, and then you might hope for the tidal disruption to show up as well in your data later on. In any case, of course, these are all multi-messenger events as well, even though until today, I think there has been no confirmed electromagnetic signal from a white dwarf tidal disruption. Okay, so in summary, we have space detectors. LISA is going to happen. We have terrestrial detectors already existing, and we have future ones on the horizon. There's a missing link that we have to provide. It is maybe the biggest challenge that is remaining in our field after the construction of LISA and the next generation terrestrial detectors. And so I think this is really where we should start to put our effort in, because that is going to be one of the technologically most difficult bands to cover, but with a huge return in terms of science, I hope. And so that's how I want to start. Thank you.
Thank you. Take one or two questions. Any questions?
I have one online.
Should I go first or do you? Okay, thank you for the nice. I was just curious about these lunar gravitational wave observatories. In terms of feasibility, how much of an issue do you think human activity like mining and drilling on the moon would become an issue?
So definitely mining, if it happens, would become an issue. I mean, it is even an issue on Earth if you are too close to it, you know, the detectors would be in trouble. So, so you have to avoid on Earth and certainly also on the moon being close to mining activities. But I mean, mining will not look on the moon in my lifetime like what we know from Earth. It will be like little things. Maybe somebody has a little shovel and is digging something out of the ground. It is not going to be like these big mining operations. There are so many challenges when it comes to lunar exploration that people do not really address in their claims. So I think we have a bit of time, but the point is still important. I mean, when you select a site for lunar detectors, you have to be sure that there's at least no activity at that site and anywhere near it. So what you need are agreements that protect sites on the moon for science. And I guess you know that there's a radio astronomy that has similar plans on the moon. They also need protection. Gravitational waves need protection, but it's not the only cases. There are also geologists who want to keep like the regolith structure pristine on the surface because it could have like billions of years of history of our solar system layered down, and so there are so many things that should be protected for science. And so people do have now committees and programs to realize some level of protection for scientists for the moon. And so we hope that this can actually be done.
Okay, nice talk. Can you go to the memory effects slide? Yeah, can you just explain it a little more, man? Sense.
So first, there are two different types of memory effects. So one is the linear and the non-linear. The linear one is the thing that is building up here. Essentially, what happens here is that when you have an asymmetric, emission, that in the end, what you get is a kick essentially of, matter is asymmetrically expelled and neutrinos in a way that essentially there is a step in the space time that propagates out. And so this step function is really what builds up here and remains. So it is, a lasting deformation of space-time, if you want, that forms together with the transient that is being emitted. So in the end, if you look at the mathematics, this is typically connected with the energy, with the integral over the energy over, that accumulates over time.
This is the burst signal as such, right? This is a burst signal with your...
So this is a burst signal, but then if you look into how this memory effect forms, it's not a burst anymore, it's really a step in space-time that propagates out. And so in the end, space-time after the waves pass is not the same as before. There's a memory.
Yeah, that's the definition, right? Yeah. That's okay. Anyway, we can discuss it.
Thank you for the talk. You mentioned that Decihertz observatories are not possible on the ground at all, that you can't subtract away the sources of noise. Yeah. So it's just simply not possible. I was wondering if A, you could just give a simple hand-waving argument for this, and B, at what frequency can you subtract away? In other words, is it at 1/10 of a hertz, at 1 hertz, at 5 hertz?
Yes, so the thing is that about how much you have to subtract. What is the factor of noise reduction that you need? So here's how we would do the subtraction. We would do what is called Wiener filtering. Essentially, we would take data, so from environmental sensors, let's say, and from our gravitational wave detector, and we would start to calculate correlations between these channels. And then if you have the correlations between all of them, between all the environmental sensors and with the detector, then you can use these correlations to form this Wiener filter. And that is the optimal way to process all the environmental data to make a prediction of the gravitational noise and to subtract it out. Now, every correlation estimate has a statistical error. And so then, if you have a Wiener filter that consists of a single parameter, or if you have one that consists of 1,000 parameters, the statistical error will grow in your output. That means the more degrees of freedom your Wiener filter has, the larger becomes the statistical error in the output. Now, if you make the numbers, then give, you can make estimates like how many sensors you need and the thing, and how many, frequency bins and so on you have to realize these, the subtraction. In the end, you are getting to Wiener filters that already for Einstein telescope, where the problem is much simpler, we have millions of parameters of the Wiener filter that have to be estimated. And so you find then you can make a very simple, calculation of the statistical error of the correlation estimates essentially. And you find that even canceling out noise or reducing it by a factor of 10 in such Wiener filters is like kind of the best you can do, like the statistical limit of how well you can subtract Newtonian noise. Now at the Decihertz band, you need like a factor 1,000 reduction of these noise backgrounds. And there's simply no way that you can ever have the correlation done, estimated well enough to do that. It's just not possible. You don't.
Factor of 10 reduction is possible at what frequency?
At any frequency. That's kind of, it's a frequency, if you want, it's a frequency, a factor 10 reduction could be done at any frequency. The point is in the Decihertz band, you need much more to see gravitational waves.
We take one question from online. Gopu, you can go ahead.
Yeah, thank you very much. Very nice talk. So the question again, the same slide here. So you are talking about linear memory as pointed out by Kip and others decades ago. But these things, are they, in order to see this for the Decihertz, do you have to have it in our galaxy?
Sorry, I forgot the beginning. I didn't catch the beginning of your question.
Yeah, so this is the linear gravitational wave memory even you're talking about,
yes,
right?
Yes.
That's a supernova. That's Kip and others clarified decades ago. So the question here, this is, the simulations are usually, the strain you're talking about happening in the galaxy, right?
Yeah, these simulations are, yes, for our, I think, it's,
10 megaparsecs.
yeah, yeah.
Right. Okay, so the reason why I'm saying is that such bursts, I mean, I need to get the numbers cranked up a bit. So we can actually look for, in pulsar timing, this linear memory events also affect the timing. So this will be the memory burst. It will manifest in individual pulsar. We won't get the correlation because this is only happening in the neighborhood, time to propagate and all that. So technically this can be cross-correlated eventually with SKA kind of pulsar timing, happening in appropriately.
Okay, thank you, Hans.